In this video, we're going to finish up the concept of expected value and get that straightened out. And then also, to do that, though, I need to talk about the law of large numbers. And I'm not going to give a formal definition for it, but instead talk about it in its big idea. And the silly way that I say this when I teach it in person is I say the law of large numbers is the law of you don't matter. Um, and what I mean by that, when I say you don't matter, is it's not about your personal experience. When you are at Disneyland, you may be the unluckiest person ever, and every single time you waited for that bus, it was 15 minutes. Regardless of when you got there, it was always 15 minutes. Um, because the law of large numbers says for every person that is like you, who is the unluckiest person on earth, there is the other person that you hate, but they are the person who is the luckiest person on earth. And every single time they step out onto the curb, that bus is pulling up right then and there. They never have to wait. And the law of large numbers says when you have enough trials, when you have enough experiences, you will approach the expected value. When you have not one person out there waiting for a bus, but 60,000 people out there waiting for a bus at Disney World. Yes, there's really that many people visiting there. 60,000 people waiting for buses every day, 365 days a year, for 30 years. The average amount of wait time will be 7.5 minutes, right? It's a lot of people. The one particular day does not make law of large numbers. One particular day, one particular dice roll, one particular event does not mean you will get the expected value. It is over a long period of time. And that is why I say you don't matter. It's not about your personal experience. That, of course, goes into the large number, but you could never possibly represent enough to create that. So that is the concept of the law of large numbers. Again, not going to formally define it, but it's just important you get the big idea. So when we talk about expected values, we're talking about millions and millions of trials, not one. Okay. Now, expected value. Expected value, we talked about that with the bus, and we had a feeling for it. But let me give you a way of actually calculating it. So what we're going to do for expected values is we're going to make a probability distribution table where we're going to have some event and we're going to have the probability of that event. And when we define this, we need to have our event defined in a quantifiable measure. So meaning something like 0, 1, or 0, well, yeah, 1, 2, and so on and so forth. Now, does it have to be counting? Of course not. Counting in an order? No, no, no. Maybe I have something like this: 0, positive 50, and negative 2. Right? It could be anything like that. Now, the expected value then is we're going to need the probabilities. So I'm going to make stuff up at random, pulling this out of thin air. Let's say the probability of 0 happening, whatever 0 means, would be 1 in 100. And then 50 maybe would be 5 in 100. And it's because it's a probability distribution table, then we know there's no other possible outcomes. So either it's going to be a 0, a 50, or a negative 2. Well, then that means they have to add up to 100. So this has to be 94. So now, how we calculate expected value? Expected value is the multiplication of the value times its probability. So we're going to do 0, because that is its value, times the probability of 0 occurring. Then we're going to do the next one. So that'll be its value, which is 50, times its probability, which is 5 out of 100. Then, last but not least, we have a third one. So that's going to be negative 2, negative 2 times its probability of 94 over 100. And we're going to take all these values and add them. Because we're going to say, I'm going to get 0, 1/100th of the time. I'm going to get 50, 5/100ths of the time. And I'm going to get negative 2, 94 100ths of the time. So now we're going to calculate these values and see what this equals. So I'm going to pause the video while I do that. And I got 0.62. So then the next key thing I want us to focus on is what does that mean? And I can't really answer that right now because we don't have a context. The next problem will have a context, so we'll talk about that. But the idea here is we get like 50 5 out of 100 times, and I get -2 94 out of 100 times. So even though 50 is way bigger than -2, because it happens so less frequently, this number was trending more towards -2. It was getting closer to that. All right, let's do one with context. This is really just to give you the formula. So what was the formula? Take the value times its probability. Take the value times its probability. Take the value times its probability. Add them all together. All right, here we go. So we want to find the expected value of the game of roulette when, because there could be lots of different expected values. It depends how you play. So what we're going to do is we're going to bet on one number, and this is the same situation we talked about last time in the notes with roulette. So if you need to, go and review that real fast. But the idea here, we're betting on one number, and I'm telling you we're playing on a table that has a total of 38 numbers, right? So I believe that would be American roulette. And when we win, we get paid $36 when we're betting $1. So that means I put $1 on the table, and if I win, I get 36 back. That includes my original $1. So here's our table. All right, you ready? So our event and the probability of the event. So when you're playing the game of roulette, there's two outcomes. You either win or you'll lose, right? But that's not how we want to define it, because we just got done saying the values have to be values, they have to be numbers. So let's assign values to winning and losing. Let's actually give them a number. So when I win, how much do I win? It's very tempting to put 36 here, but that would not be correct, because if you think about it, if I put $1 of my own money on the table and I get $36 back, I didn't really win 36. I'm really up 35, right? Because one of those dollars was my own dollar, right? And when I lose, it's a -1 because they take one of my dollars, right? So there we go. Now, what is the probability of these things occurring? Because we're only betting on one number at a time, that means out of the 38 possible numbers that could come up, one of them would make me a loser, and 37 of them would make me a winner. All right, so stop and reflect, think about those probabilities, because if you get this right, you do not mess up expected values. If you can set this table up, you always get them right. So how do we do this? All right, here we go. Hopefully that was enough time to reflect. I am going to find the expected value of my random variable. Sorry, this should be x, not e. Silly me. X, and the probability of X. I was putting E for event, but that would be kind of confusing because we're doing expected values. Okay, so yeah, so same thing up here. This should be an X. There we go. All better. So the event, the expected value. Take the value, which is 35, multiply it by its probability, which is 1 out of 38. Take the next value, which is -1, take its probability, which is 37 out of 38. And now we add these together. And the nice thing here is now we have meaning. So what does this 35 mean? Well, it means I win $35 1/38 of the time. And it means the -1 means I lose $1 37 out of 38 times. All right, so now we're going to pop that in our calculator and see what we get. So this is what I found. I get -0.052631578.9. All right, what does that mean? Right, we're playing the game of roulette. The expected value carries the same units as the things your values in your table. Those have the units of dollars, right? $35 and -$1. So therefore, this is a unit of money. This is a unit of dollars. So what we're saying here is I expect, now the negative means, since the 35 was positive, meaning I win, the negative is I lose. This means I expect to lose 5 cents, or 0.052631578.9, but 5 cents per spin. So every time I play the game of roulette, I expect to lose about a nickel. And that, when you come with that perspective, when you understand the law of large numbers, it makes it a little more fun, because now you can, it's going to balance out eventually. Where you're gonna, but you understand that you expect to lose, and you expect to lose about a nickel. All right, so that's expected value, and that's how we interpret it. The most common mistake students make is they try to tell me that this is a percentage, or they try to tell me this is a probability. No, no, it is not either of those. It is the units that you see from your original table of values, right? It gets interpreted that way. So, very similarly, if we were to do that with this, we would do 0 times 1/16, 1 times 1/16, 2 times 1/16, 3 times 1/16, and so on and so forth. And notice these all had the units of minutes, right? Everything up here was the units of 0 minutes, 1 minutes, 2 minutes. So our expected value had the units of minutes. Same idea. Okay, so let's do a couple more and then we'll be done with this video. When flipping 3 coins, how many heads do you expect to land face up? All right, so we can make a probability distribution table on this. All right, now I could write it as as heads, tails, and whatever, or just we could put a number on it. How many heads? Well, I could get 0 heads, I could get 1, I could get 2, or I could have all 3. All right, now since we're flipping 3 coins, we got to get these probabilities. All right, so the probability, how many different possible outcomes are there when we're flipping 3 coins? Well, first coin, second coin, third coin, 2 choices, 2 choices, 2 choices. So that makes a total of 8 possible outcomes. All right, how many ways are there for me to get 0 heads? There's 1 way. I get tails, tails, tails. How many ways are there for me to get 3 heads? 1 way. I get heads, heads, heads. All right, so now let's think about the in-betweeners. How many possible outcomes? How many ways are there for me to get 1 heads? Well, out of the 3 coins, I choose 1 of them to get heads, which therefore forces the rest of them, the other 2. Out of the other 2, I'm going to use all 2 of them, and I only have 1 choice. They have to be tails, all right? So all this isn't needed. It's just out of my 3 coins, pick the one that's going to be heads, so that gives me 3 possible outcomes. Similarly, 3 coins, pick 2 of them to be heads, 3 outcomes. And you'll notice that makes 3 plus 3 is 6, 7, 8. That makes 8 out of 8. So we are good to go. All right, let's clean this up. So, what is the expected number of heads? How many heads should I expect to get? Well, 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Right, so we pop that in our calculator, and what do we expect to get? Lo and behold, it's 1.5. Well, doesn't that kind of make sense? Because if we're flipping 3 coins, how many heads would you expect to get? Well, like half. Half the time it's going to come up heads, half the time it's going to come up tails. So therefore we get 1.5. Well, does that make sense? Is that answer even possible? How do you get flip 1.5 heads? Well, you have to remember, this is the law of large numbers. This is the average. So sometimes you're going to get 1, sometimes you're going to get 2, but on average it'll work out to be 1.5 heads will be flipped. Awesome. Now do that for 500. No, right? That's way too much. And so there is something I hope you recognize here. It's the binomial distribution. Do you recognize that this is a binomial situation where we could say we either get heads or we don't, right? So there is, when you have a binomial, there is a shortened version of way of calculating this, and it really just comes down to logic. The binomial says, all right, the expected value, when it's binomial, the expected value is n times p, using the same variables from the Bernoulli trials or the binomial distributions. N is the number of trials, and p is the probability of success. If I could spell the word success, I hope that's right. All right, so therefore, how many trials are we going to have in this problem? 500 coins are getting flipped, so we're going to have 500 trials. What is the probability of me flipping heads? 1/2. So therefore, our expected value is 250 heads. Do you see how amazing that is? When you recognize that you can define it as a binomial distribution, you get to skip the whole table of values, the whole probability distribution table, and just go straight to n times p. All right. So that takes care of everything I needed to talk about as far as this situation. So the next video is just an example problem and a really good one. Don't skip it. You're going to want this for some of your multiple choice classes. All right, we'll see you then.